Welcome to this MADYMO online training on multi-body modeling. In MADYMO we have three integrated solvers. We have a multi-body solver, a finite element solver, and a thermodynamic solver for modeling the gases inside airbags. In this session we will focus on the multi-body solver. The definition of MADYMO multi-body systems starts with building up a rigid body chain. A rigid body chain is a chain of rigid bodies and kinematic joints that basically forms the core of your multi-body system. In addition, rigid surfaces can be modeled to represent the geometry of the system that you're modeling. Once your system is defined, you can apply and define initial conditions, kinematic and dynamic constraints, and apply external loads. In this session we will focus on the rigid body chains, the initial conditions, and the kinematic constraints. Rigid body chains in MADYMO can be of two types. One type is a system with a tree structure, and the other one is a closed chain. In a system, an open chain system with a tree structure, basically every rigid body has only one parent joint. In a closed chain, there are multiple parts from one body towards another, as you can see in the lower right picture on this slide. In this session we will focus on the systems with tree structures. For building up a rigid body chain in MADYMO, you need the following keywords, the following element classes: coordinate system object, orientation, body, joint, and surface. On the right you see how a multi-body system looks like in a MADYMO input deck. First we focus on the element body. The element class body has three subclasses: body rigid, body deformable, and body flexible beam. In this session, for the basic multi-body chains, we focus on body rigid. In a rigid body, the body does rigid element in MADYMO, you define a body and its mass and its center of gravity and its moments of inertia. In addition, you can add a geometry, a surface to it to define its geometry. All the data in a multi-body, in a rigid body, is defined with respect to the local body coordinate system. So that means the center of gravity location, the locations of kinematic joints that are attached to the body, attachment points for dynamic restraints, and reference point locations for multi-body surfaces. All of these are defined with respect to the local body coordinate systems. Coordinate systems for instance, joints need to be defined with respect, as mentioned, with respect to the local body coordinate system, and they can be defined with the element coordinate system object. You have three subclasses for coordinate system object: the coordinate system object MB, FE, and reference, where reference is merely an indirect reference to a coordinate system object MB or FE. You see on the slide that we have coordinate system 1 or 2 dot MB, for instance. This is, we'll see this later for the joints. This is meant because for a joint you need to define two coordinate systems. In this session, for a simple rigid body multi-body chain, we will focus on coordinate system object dot MB. If you define, for instance, a joint coordinate system with respect to a body local coordinate system, it's also necessary to be able to give it a relative orientation. For a joint, for instance, you can have an axis of rotation that you want to have defined in, say, an angle of 45 degrees with respect to the local body coordinate system. And for that you need the element orientation. There are four subclasses for the element class orientation: orientation.matrix, orientation.screw-axis, orientation.successive rotations, and orientations.vector. These are basically all different ways to define a relative orientation of two coordinate systems. All can be used. Next we go to kinematic joints. Kinematic joints are what they in fact do. They constrain the relative motion of a child body with respect to its parent body. So a joint is located in between two bodies and it connects them in a kinematic way, and depending on the type of joint there are one or multiple degrees of freedom and degrees of suppression. So a kinematic joint effectively imposes constraints on the relative motion of the bodies, and when these bodies, when there's loads applied to these bodies, relative motion is tried to be given, then that will result in joint constraint loads for the degrees of suppression. As mentioned, the degrees of freedom are defined by the joint type, and it is also necessary to know that kinematic joints can be locked, unlocked, or removed in MADYMO. They can be given initial joint positions or initial joint velocities, and they can be given prescribed degree of freedom positions or accelerations. We will come back to that later. On this slide you will see how a joint is defined in MADYMO. You see we have the keyword in this example, revolute joint, joint.revo, and you have two child elements for the coordinate systems for the positioning of the joint on each of the bodies. So on the top left picture you see in red there is a coordinate system, a body local coordinate system for the parent body. And with coordinate system underscore object 1.mb, the position and the orientation of the joint coordinate system with respect to this parent body coordinate system is defined. With coordinate system object 2.mb, the location and the orientation of the child joint coordinate system is defined with respect to the child body coordinate system. So this is shown on the left side on the slide, and on the right side you see a number of examples how this can look like, where in pink you see the parent body, in blue you see the child body, and depending on the orientations that you give to the relative orientations that you give to the parent joint and the child joint with respect to their bodies, you see that when MADYMO is initialized, when you run a simulation, the body chain is assembled, and in the assembly the child bodies are basically linked to their parent body. So a chain, you can see that as a successive assembly of bodies with respect to their parent body, and the way they are assembled is defined with the joints and the orientations relative to the body local coordinate systems. Multi-body chain requirements. For every multi-body chain in MADYMO, at least one body must be connected with a joint to reference space. This is what we call the root body of a multi-body chain, and the joint that links it to reference space is often called the root joint. Each body must be a child body in a joint at least once. This is again a requirement for an open chain multi-body system in MADYMO. As soon as any of the bodies is more than once a child body, that would mean it has more than one parent joint, then MADYMO will interpret this as if there is a closed chain, and it will try to assemble it as being a closed chain. So for instance, if you by accident switch parent and child in your chain, it can be that MADYMO will not be able to assemble it. If you were intending to make a chain tree, an open tree system, it might not assemble. So you have to beware, if you want to make an open chain body, make sure that every body is just once a child body and has one parent joint. Next we go to the joints. On this slide you see a listing of the types of joints that are available in MADYMO. So it varies from the most simple one being a bracket joint, being a full constraint, a rigid constraint between two bodies, revolute joint, translational joint, universal, cylindrical, etc. Also combined joints are available, like revolute translational, translational revolute, translational universal. And in the end there's also the option to have user-defined joints in MADYMO. We will not deal with that in this session. A few joints to show as an example. You see here the joint.brac, the bracket joint. As mentioned, this is the most simple joint in MADYMO, which is in fact a rigid link between two bodies with 0 degrees of freedom. A revolute joint has 1 degree of freedom, and 1 rotational degree of freedom, of course. And you see here in the pictures on the left side, you see manual explanations of the joints, and on the right side you see also a picture from the manual. And for joints, for instance, like a revolute joint, it is important to realize what the axis of rotation is. For a revolute joint, this means the x-axis of rotation of your joint coordinate system. The x-axis is the axis of rotation. That is important to know when you design your system and you want to define how your bodies can rotate with respect to each other. The same applies, of course, for a translational joint, also 1 degree of freedom, in this case not a rotational but a translational degree of freedom. And again, you need to know which axis is the degree of freedom axis, the translational degree of freedom axis. So for a translational joint, that is also the x-axis in this example. Spherical joint is a ball and socket joint, if you like. This joint is defined with his degrees of freedom in Euler parameters. So you have a vector and 3 angle parameters. Another example, the free joint, which is basically the opposite of the bracket joint. This is a joint with 6 degrees of freedom. So as in a joint chain, every body must have a paired joint. But for instance, if you want to have a system that is can move and can rotate, translate without suppression with respect to reference space, it means that your root joint, your first joint in your chain, would be of the type joint.free. So it has 6 degrees of freedom, it can freely move into space. Next we come to multi-body surfaces. Once you have defined your multi-body chain with joints and with bodies and joints, you can also give the system a geometry. Of course, that's very nice if you want to see your system in your post-processing, see what your system does. It's nice to not only look at coordinate systems, but also see some geometry. Now, in MADYMO, you can do this basically in 2 ways. You can do this with simple analytic surfaces. We have surface.plane, surface.ellipsoid, and surface.cylinder for that. And you can do that basically with arbitrary rigid surface shapes. And these are basically finite element surface meshes that you can fully support to 1 or more MADYMO bodies. The latter you do with, as it are finite element surfaces, you do with FE model. You can leave them without mass. For that you can use material.null. You can give it properties, membrane properties, since it's 2D surfaces generally, and you can use the keyword support to fully support them to bodies. Such surfaces we often refer to as being facet surfaces. Surface.plane or surface.plane center is the baseline mathematical surface that you can use for, as mentioned, planes. So there's 2 ways of defining them. Surface plane is the original one. More recently, we have built in the surface.plane center. which has a definition that is more equal to the surface.cylinder or surface.ellipsoid, where you define a center point with respect to a body, and then you define its half length in two directions. Whereas the original surface.plane is defined with 3 points with respect to the body directly. But if you want to control the orientation of a plane with respect to its body, it's often more user-friendly to use the surface.plane center. The surface ellipsoid, basically it is called ellipsoid, but it can also be a hyperellipsoid. On the top right of the slide you can see how a surface ellipsoid would look with degree 2. With degree 2 it's a normal ellipsoid, but if you give it a higher degree, like degree 4 or degree 8, you will see that the shape of the ellipsoid becomes a hyperellipsoid, and the higher your order is, basically the more it will look like a box, a cube. The formula that defines the surface is given on the slide as well. And an example is given on how you define it in MADYMO with surface.ellipsoid. And the connection to a body is done with coordinate system object 1 dot and b. And the same applies for a cylinder. A cylinder is similar than an ellipsoid, but only in 1 degree. Basically, your semi-axis is infinite. So also there you can have second order and higher order ellipsoids, and the higher the order, the more square shaped your ellipsoid or your cylinder will be. This about the rigid body change and its geometry definition. Next we will move to the initial conditions. Initial conditions on a rigid body system, on a multi-body system, are basically defined with joint initialization. For that you can use initial.joint pos, initial.joint vel, velocities, or initial.joint status. So the positions and the velocities can be initialized, and the status means whether that initially you can set the status of a joint to lock or to free. So for instance, if you have a revolute joint, you put it to free, it means that the two bodies can freely move around the defined axis of the revolute joint. But if you put it to lock initially, it means that they are rigidly, kinematically connected, the two bodies. Now, what happens exactly if you do the joint initialization with initial joint pos is you can see that here. In the lower left plot, you see an example of a revolute joint being initialized with an angle of, I believe it's 30 degrees. Now, the upper left plot shows how the joint is positioned in reference position. If a multi-body chain in MADYMO is assembled, it always means that the child joint coordinate system is projected exactly on the parent joint coordinate system. So that is basically the reference configuration of your body chain. And if you want to change that, you can do that with joint initialization, with initial joint pos. Or in the example here, lower left, you see that the initial value is directly given in the joint. That is also a possibility with R1 in this example. And once you define a value that is different from 0, that means for a revolute joint, for instance, that the child joint coordinate system will rotate with this given angle in radians with respect to the parent joint coordinate system. And that is what is shown in the right plots. Here you see the joint orientation can be, as long as the coordinate systems of the joints are on top of each other, it means reference position. It's basically a system definition. This is my reference position of my joint. And with initial joint off, you see a rotation appearing between the two joint coordinate systems. Finally, something on the kinematic constraints that can be applied. Kinematic constraints on a multi-body system can be applied. Well, they are basically already applied with the definition through the degrees of suppression. So if, for instance, you have a revolute joint, it means that there is 5 degrees of freedom between the two bodies that the joint connects. There's also already no motion possible. There's no translational motion, and the two rotational degrees of suppression also prevent the bodies from rotating relatively in that axis. So those by themselves are already kinematic constraints to your system, if you like. On top of that, you can switch the joint states, or you can even completely remove joints during your simulation. So those are changing constraints during your simulation. So with joint state switching, we mean the switching between lock and free. And finally, there's also, you can have basically a static kinematic constraint by locking it in a certain configuration, but you can also have a kinematic constraint with a varying joint degree of freedom value, and you do that with a prescribed joint motion. So the joint state switching is done with state.joint, and you use a reference to a switch element. That can be a switch in time or switch based on a sensor, whatever you like. You can define and change your state during your simulation. The state joint remove, what it effectively does is that it changes once you can do that one time with a switch, and once that is activated, it means your kinematic joint will change from whatever its type was, for instance revolute or translational. It will basically change to a free joint. It means that once a state joint remove is activated with a switch, all degrees of freedom between the two bodies will be released, and the child body can move freely with respect to the parent body. If there were joint restraints defined on that specific joint, also the joint restraints will be removed. As mentioned, for the joint state switching or joint removal switching, you can use switch elements. There are several switch types available in MADYMO. The most simple one is the switch.time. Basically, then you just say at a specific time in your simulation, you will activate the switch. So it's directly defined by the user. But there's also, as mentioned, switch sensor, for instance, that you can define your own sensor in MADYMO to trigger the switch on a certain threshold level for an acceleration, for instance. And you see several other switch types like switch control system, switch logic, switch multiport. All these can be used to set up a more complex switch logic applying on, for instance, in this case, a joint state or a joint removal. The second type of kinematic constraint that I mentioned was prescribed joint degree of freedom motion. You can do that in two ways. It's kinematic constraints either by motion joint pos or motion joint ac. So it's in both ways it's still kinematic. The motion is prescribed, but you can do it in terms of positions or prescribed accelerations. So you will use functions for that to refer to so you have a function of the degree of freedom, position or acceleration versus time, and you refer to that in motion joint pos, for instance. And for every degree of freedom that you have no function defined, in motion joint pos, that means that the joint position is kept to 0. In motion joint ac, it means that the acceleration is kept to 0. That was the end of this session. Thank you very much for your attention. Bye-bye.